Hello and welcome to this video. Here in this final section, we'll be looking at how circles interact with triangles and what assumptions you can make to solve geometric problems. Before we go any further, I must point out that in the last video, I discussed with you some to solve questions in exercise 6E. Some of the questions from exercise 6E, namely question 8, are rather challenging, and question 19. So I suggest if you haven't had a go at them, pause the video, go ahead and work through questions 8 and question 19 in exercise 6E, and then I'm gonna simply show you the working out. I've taught you this method in the previous video, so I'm not gonna talk about the solution here. I'm just gonna show you how it's done, and you can pause the video and then play the video next. So here's the working out, and I've tried to color code things for you to understand. We use the discriminant here of the equation of the red line here, and I've changed my pen color so you understand that the equation written in black down here is completely different to the equation of previous lines, so don't confuse one with the other. We're just using the fact that the discriminant is equals to 0 here for the tangent to solve the point where the line meets the circle. There is some rather complicated algebra in the red box on the right side here. I've expanded terms. It's rather complicated, but if you think about 5 minus p as one term here and put a bracket around it and just multiply out the brackets, you end up with such an expression that involves x's and p's. So yes, rather hairy, but and this is question 19 again. I didn't see any simpler answer than what I've come up with. So pause the video if you haven't done it. I'm just going to play the solution next. So here's the solution to this problem, and the final answers turn out to be the grade. We were finding out the gradients. One is a quarter and the other one is negative 4, and they're perpendicular to each other because, well, this is a square here. All right, so we figured out what's the gradient of L1 and L2. All right, so now in this section we go to what you need to know to solve questions from exercise 6F. If we have a triangle here, and if we bisect each of the sides of the triangle here, and we draw the perpendicular bisector to each side of the triangle with this log that you could have learned, and you should have learned in GCSE level. So what you notice is that these perpendicular bisectors all meet at one point, and that point is where, if you put your center of your compass around the triangle, you figure out that that blue circle touches the each corner of the triangle there. All right. So what does that really prove to us? That's another proof that when you have chords of a circle, imagine that that black line there, side of the triangle, was just a chord. So uh, even if you had another triangle here, the perpendicular bisector of any chord, any two chords, will meet at the center of the circle. All right. So that's uh, that's one of the proofs that we will use in future examples. So again, one more time, these two red lines are the chords of the circle, and their perpendicular bisectors meet at the center. Now, triangle, each side of the triangle, you could consider it as a chord, and if you've been told that the one side of a triangle is the diameter of a circle, then the other two sides, what can you assume about it? If we've been told that, let's say, A to B is the diameter of the circle, then we can assume that this angle is automatically a right angle. There's circle theorems for you. If you remember, an angle at the center of the circle Here, this angle is 180 degrees, so half of it would appear there as 90 degree, wouldn't it? That's coming from circle theorems. So now here in this example, we've been told about coordinates of the triangle here, and we've been told that lies on a circle. So we're sure that these coordinates are on the circumference of a circle, show that AB is a diameter. Now, there are various ways you can do it. There's two ways. You can find the gradient of A to C and show that it's perpendicular to the gradient of C to B. But that's one way, the gradient method. If you prove that these two lines are perpendicular to each other, then the third line here is of circle. You can use circle theorems in reverse to say that circle by circle theorems that's true, or you can use the distance formula. All right, so it's up to you. So with Pythagoras theorem, you can find the distance between A to C and the distance between C to B, and finally figure out the distance between A to B with Pythagoras theorem and show that these values meet the Pythagorean theorem. So that means that just to show that A to C square plus C to B square is equals to, you need to show what it is. So that would be 80 when you square that, and that would be also another 80 when you square root of 80, and that's is 160, and that is b to a square or a to b square. Now, if that's a to b square, then a to b is the square root of 160 with just from these two with these two facts. So then that works out to be the same. Uh, you just didn't know what the answer was, but the answer comes out to be, sorry, that's 160, not 190. All right. So all right. So that's using the Pythagorean theorem with circle theorems. Okay. And then now in the next part, we've been asked in part B, say we are looking to find the equation of the circle. All right. So what's the equation of the circle? If A to B is the diameter, the midpoint is the center of the circle, and if the A to B's diameter, then radius is the square root of 160 over 2. So that's, and r squared therefore is 160 over 4. Sorry, yeah, 160 over, when you square both sides, you get 40. Okay, so what we're going to do is figure out the midpoint of A to C, and radius we already know what it is. I showed you up there in the corner top. So we're figuring out, going through the calculations from midpoint, and we get -2 and 3 here. And now we're gonna put them into the equation of circle. You write x minus a -2 makes a +2, and you put a square on it, and then you say y minus 3, and you put a square on it, and you write that's r squared. What's r squared? R squared is 40. Now you can uh, write 162 over, and you get 40. All right, so that's this example done. Next example is saying the coordinates P, Q, and R lie on the circumference of a circle. The The equation of the perpendicular bisector of PQ is y equals to 2x. Find the equation of perpendicular bisector of PR. Okay, so PQ and PR. We know, so what we know the gradient between P to Q then equals to 2, and then because it's on the circumference, let's just sketch the circle. So they're not perpendicular in any shape or form at the minute, but we know the perpendicular bisector of PQ. I didn't write that carefully, So perpendicular bisector P2Q is 2x, not not the gradient here. We don't need to figure out. So what we need to do, we kind of help somehow if we didn't know how to figure out us to figure out the perpendicular sector between P to R, and then that will help us to calculate what the equation of the circle is finally. So really, they kind of stage the problem for us so that we earn some marks even if we don't know how to calculate the equation of a circle straight away, so that we are basically going to figure out this gradient of the green line joining P to R. So using the perpendicular, the gradient here of P to R, then we're going to figure out its perpendicular bisector and finally figure out where the two orange lines meet each other. So finding the equation of perpendicular bisector of P to R involves figuring out its midpoint as well. So that's why we're going through the midpoint formula here. So the midpoint of P to R is minus 2, 11. It geometry makes sense for it to be minus 2 and 11 in that quadrant. Then the gradient of P to R is simply dy by dx, a change in y divided by change in x, and we get a 1. So the negative perpendicular to it is negative 1. The gradient of the orange line is minus 1. Minus 1 have to intersect. So now we're going to, next stage is to figure out where is this intersection point here, because we need it to for the center point of the circle. We already know one equation has this formula. We kind of need to know the equation of the other line before we can find the intersection point. Otherwise, we can't find it. So we do need to use the y minus 11 equals to minus 1 times x minus 2 makes a plus 2. So multiply this out, minus x minus 2, and then add 11 to that. And we write y is here, simplifying, we get plus 9. So the equation of this line here is y equals minus x plus 9. And as you see here, it makes sense for the intercept to be positive. So now we're gonna simply set these two equations equal to each other and solve it. That's not hard to do. 2x equals minus x plus 9. Add x to both sides, we get 3x here equals to 9. X is 3. Therefore y is 2 lots of 3, 6. So although it's not drawn accurately, why is the y value 6? If I substitute that 3 into either equation, I'm going to get y 6. So the picture isn't drawn accurately, so don't blame me for that. It doesn't be accurate. Okay, so we figured out the center of the circle, and what else do we need to know? We need to know the radius of a circle. How do we figure out the radius of a circle? You can because you know the center is 3, 6, doesn't matter which coordinate you use. You just need to figure out the distance between any of these coordinates, the distance between any of them. So that we've taken 11 and 12. So we've taken the C and Q, the distance between C and Q to find R. R is 10. Finally, what we're going to do, we know everything to write the equation of the circle. Work out, because part C was saying figure out the equation of the circle. So part B was asking us to figure out the center of the circle, and now we did that. Center was 3, 6. So we're going to write x minus 3 squared plus y inside the bracket, y minus 6 square equals to 10 square is 100, and we write it like so, and that's it. That's the equation of the circle. Notice